this impulse thing is also really useful if we look at in a collision. Between object A and object, and I'm actually going to go back and make that a capital A, object B. We want to look at what will delta P be for each object. So delta P for object A will be a result of the force of object B on object A over the time period of the collision. So force of B on A, and this is the duration of the collision. Some of you might already be intuiting what, or recognize what's coming. If we look at the change in momentum of object B, that's going to be a result of the force of object A on object B times the change in time. I think you'll all agree that the time for the duration of the collision is going to be the same for both objects since they're colliding with each other. This is the force of object A on object B. And what we know from Newton's third law is the force of B on A is equal to the negative of the force of A on B, because for every action there's an equal and opposite reaction, or because if object A exerts a force on object B exerts a force on object A that is equal in magnitude and opposite in direction. Or A pushes on B just as hard as B pushes on A, which means delta P for object A is equal to the negative of delta P for object B, which means the total change in momentum, which is the change in momentum of A plus the change in momentum of B, is equal to the change in momentum of negative that plus positive that, which is 0. So in the collision, the total change in momentum is 0, which means momentum is a conserved quantity. And that's a big deal. And I didn't mean to draw a line through it, I meant to underline it. So momentum is a conserved quantity. In a collision, P total initial equals P total final. If we talk about two objects, collision between A and B, we would have MAVA1 plus MBVB1 equals MAVA2 plus sorry, those should be B's, MBVB2. And this is the conservation of momentum equation. which is the thing that's really useful in analyzing collisions. And we'll look at some problems on Thursday where we see how this formula is useful in analyzing collisions. It's really important to note that um, while energy is conserved, kinetic energy is not conserved in a collision. If you have two cars heading toward each other and they slam into each other, there's not as much kinetic energy after the collision as there is before, because the cars either stop or are moving backwards or whatever. But the total kinetic energy is not conserved, whereas the total momentum is actually conserved. In the instant after the cars collide, they will have the same momentum together as they did if you put their momentums before the collision together. And that's crash scene investigators use that all the time when analyzing the crashes between cars or whatever. Now that we know momentum is conserved in collisions, we're going to look at specific kinds of collisions and see how this conservation of momentum equation applies in particular situations, kinds of collisions. And there are basically three kinds. There's an elastic collision, where the objects move or don't independently. You have to spell that right. Independently after the collision. And in that case, we just have, it's possible that both objects are moving before the collision, so we'd have MAVA1, MBVB1, and after the collision, we'd have both objects potentially moving after and independently. So if we know everything before the collision, we'd have two unknowns after the collision, those being the two velocities. So really, because we just have this one equation, we have to know something about one of the objects after the collision to be able to figure out the other one. And the other kind of a collision is an inelastic collision, where the objects are stuck together and move or don't as one object after the collision. And in that case, we'd have MAVA1 plus MBVB1 equals, and after the collision they'd be stuck together, so we'd have MA plus MB times V2. So in the case of an elastic collision, we can solve for one of the velocities, and in the case of an inelastic collision, we could solve for the final velocity if we knew the two velocities beforehand. And then there's, so these are the two kinds of collision. And then there's also technically an explosion, where objects are at rest before the collision and move away from a common center. And then you'd actually have, there's no momentum beforehand. And unless you have things that are moving before the collision, before the explosion, which would just be adding unnecessary complexity. So we'd have 0 equals MAVA2 plus MBVB2. So those are the collisions and explosions. Now there's one problem that I mentioned before, which is for in an elastic collision, one equation means only one unknown can be found after the collision. However, there are technically two kinds of elastic collision. There's what's called a perfectly elastic collision, where kinetic energy is conserved. In which case we have also 1/2 MAVA1 squared plus 1/2 MBVB1 squared equals 1/2 MAVA2 squared plus 1/2 MBVB2 squared. Along with conservation of momentum, MAVA1 plus MBVB1 equals MAVA2 plus MBVB2. So we have two equations. Can find two unknown velocities. So there's perfectly elastic, and then there's imperfectly elastic, where kinetic energy is not conserved. And in those cases, there's something which is called the coefficient of restitution, which is an experimental quantity that measures how velocity is distributed in a collision. And there's a derivation for it, which in years when we're taking more time, I've gone over. This year, I'll put a link to it in the homework stuff, and you can read over it, and those who are interested, and you can ask me questions in class about it. But the formula, it's the coefficient of restitution, has the symbol E, lowercase e, and it's V, it's actually negative, V A2 minus VB2 over VB1 minus VA1. And that's the coefficient of restitution. And as I said, it's an experimentally determined value. And it turns out that for a perfectly elastic collision, E is equal to 1. For a perfectly inelastic collision, where the objects stick together, there's no relative velocity after the collision, and we have E equals 0. And all others, which is really the majority of collisions, E is greater than or equal to 0 and less than 1. Or really, so really for all collisions, it's greater than or equal to 0 and less than 1. But for others, it's between 0 and 1. And so then we would have two equations again. So now we have two equations. E negative V A2 minus VB2 over V B1 minus V A1. And the conservation of momentum, which we'll write again because it's so much fun. V MAV A1 plus MBV B1 equals MAV A2 plus MBV B2. Which means we can find two unknown velocities. So we'll deal with all of this stuff in class on Thursday and Friday, as much as we're going to deal with it. And you'll have a chance to look at some concept questions about these things and do some problems, and we'll look at some actual collisions with the carts on tracks, and you can mess around with E, and we'll do all kinds of work with this on Thursday and Friday. Thanks for watching, and I'll see you then.